Good morning, cadets. We have learnt about the zeroth law of thermodynamics and we have defined what is temperature. Temperature is the one which determines the thermal equilibrium. When the two systems are in thermal equilibrium, then their temperatures are same. This is how we concluded using zeroth law of thermodynamics. Right? Now, temperature is the marker of hotness of a body. Temperature is the marker of hotness of a body. When two systems are brought in thermal contact, then it decides the direction of flow of heat from one system to another system. When there is a temperature difference between these two systems, then the temperature decides, the temperature of the hotter body and the temperature of colder body decides the flow of heat. The heat flows always from a body at a higher temperature to a body at lower temperature when they are in thermal contact. This is how we define what is temperature. Now we will discuss about very important things, that is internal energy, heat and work. Right? Before we go into the details of heat and work, let us first study what is internal energy. Internal energy of a bulk system is the sum of potential energies and the kinetic energies of the molecules of that system. Internal energy of a bulk system is the sum of kinetic energy and potential energy of the molecules of the system. This internal energy of the system is denoted by U. U is the notation for internal energy of the system. Then the internal energy is going to be defined as a state variable. This internal energy, although we say that it depends on the potential energies and the kinetic energies of the molecules, when we actually think of a system of gas, then it mainly depends on the kinetic energies of the random motion of the molecules of that gas. Because if you look at the intermolecular attractive forces of the molecules will lead to the potential energy of the molecules. The internal attractive forces, intermolecular forces of a gaseous system is negligible. Intermolecular attractive force of gaseous molecules of a system is negligible. So potential energy of a system of gases is negligible. So mainly the internal energy of a system of gas is determined by the random motion of the molecules of that gaseous system. So random motion results into kinetic energies. If the kinetic energies of the molecules of that system increases, the internal energy of the system increases. I think you got the point. Then the internal energy depends on the state. It depends on the state variables. You know the thermodynamic state variables of a system: pressure, volume, temperature. For a given mass, of a gas, in a system, the pressure, volume and temperature describe the state the thermodynamic state of the system. Therefore, pressure denoted by P, volume denoted by V, and temperature denoted by T. P, V, T are called as thermodynamic state variables because they describe the state of that thermodynamic state of the system. Therefore, P, V, and T are called state variables. State variables. The internal energy of the bulk system also depends on these state variables. Internal energy U of the system depends on the values of these state variables. Depends on the values of these state variables at that particular instant. How they are arrived to that instant, it is immaterial for the internal energy. For a particular system, if we know the value of pressure, volume and temperature, using those pressure, volume and temperature, one can get the result of internal energy. So internal energy depends on these state variables, and internal energy is also going to be the state variable of the system. In this way, internal energy although depends on the kinetic energy and potential energy of the molecules of the system, it mainly depends on the state variables, since it is a macroscopic concept. Internal energy, as we have discussed earlier, thermodynamics is a macroscopic science, depends on these state variables such as pressure, volume, temperature, composition and the internal energy. Therefore, internal energy of the system depends on the values of these state variables. That's how we are saying that internal energy is a macroscopic concept, although it depends on the sum of kinetic energies and the potential energies of the gaseous system. Then it does not depend on the way these state variables are arrived. It depends on those values at that particular state, at that particular instant. How the values of P, how the values of V and how the values of temperature are arrived, it does not depend. It just depends on P, V and T at that particular instant. So, the internal energy does not depend on the path, the way these thermodynamic variables are arrived. It depends only on those values at that particular instant. Then, internal energy is mainly due to kinetic energy for a gaseous system. The internal energy mainly depends on kinetic energies mainly depends on kinetic energies of the molecules. We make it as a point. These are points. Kinetic energies of the molecules, neglecting potential energies. Electric potential energies, since intermolecular forces intermolecular attractive forces are very weak. Therefore, it depends only on the kinetic energies of the molecules. Later on, we will come to know that the kinetic energies of the molecules is mainly due to random motion of the molecules. Random motion of the molecules. When a system is having a gas of certain mass, the gas molecules will never be at rest. They will be always in random motion. The random motion may be translation motion of the molecules as a whole, may be rotational motion of the molecules, translation motion, rotational motion, and vibrational motion of the molecules. So these are the three types of motions which are contributing for the random motion, and in turn they are contributing for the kinetic energies of the molecules. So mainly translational, motion of the molecules, rotational motion of the molecules, and vibrational motion of the molecules. These three types of motions are contributing for random motion of the molecules, which is in turn lead to increase in the value of kinetic energies of the molecules, and thus that will in turn lead to the value of internal energy of that system of the molecules. Okay, this is about internal energy. Next, we should speak about what is heat and what is work. You know, heat we have already defined. Heat is the energy in transit. Heat is the energy in transit. When a system is having certain high amount of internal energy with respect to surroundings, then there is a possibility that this internal energy lead to transfer of what is known as energy in transit. The energy in transit is called as heat. Okay, so we should clearly define what is heat. A system has certain amount of heat is a meaningless sentence. A system has certain amount of heat is a meaningless sentence. Rather than certain amount of heat is supplied to the system is the meaningful sentence. Certain amount of heat is supplied to the system so that the system absorbs the heat. Or on the other hand, certain amount of heat is released from the system. Certain amount of heat is given out from the system. This is a meaningful sentence. So heat is always the thermal energy that is in transit, that is always flowing from hot body to cold body, hot body to the cold surroundings, until both of these bodies attain same temperature. Okay, let us now define heat and work in detail. So heat is the thermal energy in transit from hot body to the cold body due to temperature difference. So the energy which is transferred from hot body to the cold body is called as heat. So heat is not a state variable of a given system. Therefore, heat is not a state variable of a thermodynamic system, whereas internal energy is a state variable of a thermodynamic system, whereas internal energy you can describe the state of a thermodynamic system. Therefore, internal energy is a state variable. So, we should not use the term wrongly, like a given system of given state of a gaseous system. A given state of gaseous system has certain amount of heat, has certain amount of heat is a wrong sentence. It is meaningless sentence. It is a meaningless sentence. Similarly, a given state of a gaseous system has some amount of work. That is also meaningless sentence. Similarly, this is wrong. Similarly, given state of a gaseous system has some amount of work is also wrong statement. This is also meaningless. So rather than this, we can say that a given state of a thermodynamic system is absorbing the heat or releasing the heat. A given state of thermodynamic system is supplied with heat or absorbed with heat. It is a rather correct sentence. So we can say a given system is supplied with heat because the heat is the energy in transit from hot body to cold body. So given system, a gaseous system is supplied with heat, or a gaseous system is releasing heat to the surrounding. That's a correct way of defining what is heat. So this is correct way of stating the heat. Similarly, a given state of gaseous system is doing work in expansion, is doing work on the surroundings, or a surrounding a given system of gases, gaseous system is being done work on it. Suppose a gaseous system is there provided with movable piston. If we allow the gaseous system to expand, then the piston is pushed apart. When the piston moves apart, then the work is done on the surrounding. So the work is done on the surrounding by the system. I think you got the point. In another way, if we push the piston inwards, then what happens? The gaseous system is under high pressure. Then work is done on the system. So in this way, we need to use the notion of work as either work is done by the system on the surroundings, or work is done on the system by the surrounding. So that is the correct way of writing the Notion of work. During expansion, work is done by the system on the surrounding. During compression, work is done on the system by the surrounding environment. So this is how we need to use these terms: internal energy, heat and work carefully. Heat is not the actual content of the body. I think you got. Heat is the energy that is transferred. In the same way, amount of work is not content of the system. Either work will be done by the system on the surroundings, or work will be done on the system by the surrounding. So we conclude that heat and work are not thermodynamic variables. Therefore, heat and work are not state variables. Heat and work are not state variables. This is important. So only state variable in this case is internal energy. Internal energy is a state variable which can describe the thermodynamic system. Therefore, it is a state variable. Whereas heat and work are not state variables. Okay. Now let us study how the internal energy of a system can be increased or decreased. How internal energy of a system can be changed. Let us see. Now let us learn what are the ways by which one can change the internal energy of a given system of gas. Consider a system of gas having certain amount of mass. Consider a system consisting of a gas of certain mass, fixed mass, taken in this cylinder, provided with movable piston. A system of a certain mass of gas taken in a cylinder with movable piston. If this system is taken in contact with the body at higher temperature than the temperature of the system itself, suppose it is kept in contact with a hot body, kept in contact with a source of heat, then what happens? On receiving the heat from this body at higher temperature, the random motion of the molecules increase. The kinetic energy of the molecules on receiving the thermal energy from the hot body, the kinetic energy of the molecules increases. When the kinetic energy of the molecules increases, we say that the internal energy of the system increases. This is one way of increasing the internal energy. Another way is, take the same cylinder, no need to take any hot body in contact with it. If this piston is pushed inwards, earlier the piston is at this position. This is the movable piston with the piston rod. Now consider the system of same amount of gas, same mass of gas. If this piston is pushed inwards, when the piston is pushed inwards, say this is the next position of the piston. As a result, what happens? The molecules are compressed. The volume of the molecules, volume of the gas is decreased. When the molecules are compressed, then there will be more and more number of collisions taking place among the gaseous molecules. As a result, what happens? The kinetic energy of the molecules again increases and internal energy of the molecules increases. So, by moving the piston inwards, we have done work on the system. By doing the work on the piston means by pushing the piston inwards. Pushing the piston inwards, work is done on the gaseous system. So, by doing work on the gaseous system, by compressing, the temperature, I mean the internal energy of the system increases. So, these are the ways by which the internal energies of a given mass of a system of gas can be increased. First, if the system is brought in contact with a body at high temperature, like source of heat, body at high temperature, then on absorbing the heat, on absorbing the thermal energy, kinetic energy of the molecules increase, thus internal energy increases. This is one way by bringing in contact with a body at higher temperature than the temperature of the gaseous system. This is cylinder with movable piston. Second one is by pushing the piston inwards. By pushing the piston inwards. By pushing the piston inwards, work is done. Work is done on the gaseous system. When work is done on the gaseous system, then due to frequent collisions, the kinetic energy of the molecules increases. Due to increase in kinetic energy of the molecules, the internal energy increases. So, in both the cases, we have discussed about increase in internal energy. Now, other way also we can think of, if the same system of gases is brought in contact with a body at cold temperature, a body at lower temperature. If this gaseous system is brought in contact with a body at lower temperature, then what happens? There is a transfer of thermal energy from the system to the colder surrounding, to the cold system. As a result, what happens? Due to loss of thermal energy, the molecules of the gaseous system lose their energy, and thus the kinetic energy of the molecules of the system decreases, internal energy of the system decreases. So this is one way of decreasing internal energy. Second way is, if the work is done by the system, suppose now it is kept in such a way that now due to the expansion of the gases, the piston is pushed up. The piston is pushed up and work is done on the surrounding. If the work is done on the surrounding, expansion of the gases take place. As a result, the collisions among the gaseous molecules decreases. When the collisions among the gaseous molecules decreases, the kinetic energy of the molecules decreases and internal energy of the system decreases. So, if we can say that heat is supplied to the gaseous system, the internal energy increases. This is one way. Second one, if work is done on the system, internal energy increases. This is the two way of increasing the internal energy. Second aspect, how to decrease the internal energy. Second aspect, if heat is taken out from the system, it means if the thermal energy is released from the system to the cold surrounding. If the thermal energy is released from the system to the cold energy, then internal energy of the system decreases. And second one, if the work is done by the gaseous system on the surroundings, if work is done by the gaseous system on the surroundings, then internal energy of the system decreases. Thus, we can attain change in internal energy by these two ways. So, change in internal energy is denoted by delta U. So, now we are relating heat, work and internal energy. We need to relate them so that we can discuss about the conservation of energy, conservation of total energy, right? Law of conservation of energy. Now you have understood the correct notions of heat, work and internal energy. See, heat and work are the two modes of transfer of energy. Two modes of transfer of energy. Okay, so one need to understand these three things very clearly so that we can understand the laws of thermodynamics very clearly. Okay, now let us see again the same system of gas, of certain amount of gas taken in a movable cylinder, taken in a cylinder fitted with movable piston, cylinder fitted with movable piston, right? And if it is kept on a source of heat, if it is kept on a source of heat, or if this system is now kept in contact with the body at high temperature, then there is a supply of heat. Let delta Q be the supply of heat from the source to this system. Then this will be found in increasing the kinetic energy of the molecules. As a result, it will increase the internal energy of the system. Increasing internal energy of the system is denoted by delta U. And after a certain time, you will find the piston is pushed upwards. The piston is pushed back. So if this is the initial position of the piston, then because of the supplied heat, because of the supplied heat and because of the supplied thermal energy, the piston is pushed back with certain amount of force. So force is applied on this piston in expanding through a small distance, let us say B. So work is done on the piston. Work is done on the piston by the gas. Work is done by the gas on the system, or work is done by the gas on the surroundings. So there is a relation between the heat supplied with increase in internal energy and work that is done. So this work done is denoted by delta W. So if you look at this from the point of view of conservation of energy, the amount of heat supplied is utilized in increasing the internal energy and in doing the work. So that is what we call as the first law of thermodynamics. If delta Q is the amount of heat supply onto the system. Heat supplied to the system. Delta U is the increase in internal energy or change in internal energy. Increase in internal energy or change in internal energy. Delta W is the amount of work done. Amount of work done by the system on the movement of piston. That is what we call as work done by the system on the surroundings. Then using principle of conservation of energy, we can relate this. The amount of heat supply delta Q is going to be the sum of change in internal energy and change in work done, that is work done on the system. So this becomes the first law of thermodynamics. So first law of thermodynamics is stated as like this: if certain amount of heat is supplied to a system of gas, then this supplied heat energy partly goes in increasing the internal energy and partly it is utilized in doing the work on the surroundings. So that becomes the first law of thermodynamics. This is called as equation for first law of thermodynamics. So we can write the statement now. If delta Q is the amount of heat supplied to a system of gas, then partly it is used to increase internal energy delta U and remaining part partly is utilized in doing work. It is delta W in doing work by the system. On the surroundings. So this becomes statement of first law of thermodynamics, which is in accordance with law of conservation of energy. Heat supplied delta Q is utilized in increasing the internal energy plus work done by the system on the surroundings in pushing the piston outwards. So this is how we relate heat supplied with internal energy and work done. So from this we can write what is the value of internal energy. So delta Q minus delta W gives us the increase in internal energy. Delta notation, as you say, we have been using it from the beginning. Delta notation is to represent the change, either increase or decrease. It is denoted by delta. Delta means change. So heat supply is equal to internal energy, change in internal energy plus change in work done on the system. Okay, this becomes the first law of thermodynamics. Now, here heat and work done are not state variables. They are the two modes of transfer of energy. So, internal energy of a system can change through delta U can change through two modes of transfer of energy. What are the two modes of transfer of energy? Heat and work. Therefore, understand, heat and work are not state variables, whereas internal energy is a state variable. Okay. If pressure of the system is kept constant, suppose pressure of the system is kept constant and there is a change in volume from V1 to V2, then work done can be calculated. So, if P is constant and volume changes from V1 to V2, then work done at this constant pressure, delta W can be calculated as force into displacement. Here we don't know how much is the force, but we know the pressure. So pressure multiplied by the area of that piston. If you consider area of the piston as A, right, then pressure into area gives us force, because pressure is equal to force by unit area. Therefore, force is equal to pressure into area. So pressure into area into the distance. Suppose d is the distance, d is the length through which it is raised. D is the distance through which it is raised. Then the area of the piston surface into the distance through which it is raised gives us volume. So that volume can be equal to V2 minus V1. That volume will be what we call as P into delta V. P into delta V is the change in volume. So that volume can be now written as final volume minus initial volume. So that is P into V2 minus V1. Therefore, finally we can write in general delta W is equal to P into change in volume if pressure is constant. Now, the first law of thermodynamics now becomes, therefore, when pressure is constant, then first law of thermodynamics becomes delta Q is equal to delta U plus P delta V. This becomes the equation for first law of thermodynamics. P into delta V, equation for first law of thermodynamics. So in the later part, we will discuss what happens if there is no change in internal energy. If there is no change in internal energy, if delta U is equal to 0, then what happens? In that situation, what happens? The entire heat supplied will be utilized in doing work. Delta Q becomes equal to delta W. That is what we call as isothermal process. If in a process delta U is equal to 0, delta U is equal to 0 means there is neither increase in internal energy nor decrease in internal energy. U remains constant, or U is equal to constant. Then, using the first law of thermodynamics, delta Q becomes entirely equal to delta W because delta U is 0. Such a process where there is no change in internal energy of the system remains constant. Such a process, such a thermodynamic process is called as isothermal process. Isothermal thermodynamic process. Here the pressure is constant, we can say that it is a isochoric process. Okay, we will learn about these different types of thermodynamic process in the next video, and we will calculate the work done. Okay, thank you, have a nice day.